Welcome to the Explainer. Today, we're doing something really cool. We are taking the pages of a classic grade 10 chemistry textbook and transforming them into the hidden, dynamic story of the elements that literally make up your everyday life. I am so excited to guide you through this, visually unpacking the fundamental concepts of organic chemistry, inorganic compounds, electrochemistry, and the massive industrial applications that build our modern world. So, let's just dive right in.
Okay, so, do you believe in a special life force? I mean, it sounds like something straight out of a fantasy novel, right? But here's a fascinating historical mystery for you. Early chemists actually believed that living things possessed this magical, vital life force. They were absolutely convinced this mysterious energy was strictly required to create organic compounds, and that we humans could never, ever synthesize them artificially in a lab.
But, this perfectly illustrates how science evolves. A chemist named Friedrich Wöhler came along and completely shattered that whole belief. By artificially synthesizing a compound called urea from totally inorganic starting materials, he essentially caused the downfall of the entire life force theory. It proved, once and for all, that the chemistry of life is something we can actively study, understand, and recreate ourselves. No magic involved whatsoever.
Now, we are pulling all our facts today straight from a classic 10th grade textbook. And what's kind of funny is it even comes with these nostalgic, practical rules printed right at the front, like making sure you wash your hands before turning its pages and always keeping the book in a clean, dry place. It's just a wonderful little reminder that foundational knowledge requires care, both in how we handle the physical books and how we digest the information.
To keep things organized today, here is our roadmap for decoding the universe. 1. The magic of organic compounds. 2. Inorganic minerals and crucial assets. 3. Electrochemistry and generating power. And 4. Chemistry in everyday industry.
Section 1. The magic of organic compounds.
So, organic chemistry is entirely focused on compounds containing the element carbon. Now, sure, there are a few exceptions, like carbon dioxide or carbonates, but generally speaking, if it's an organic compound, carbon is absolutely the star of the show. This encompasses all those substances derived from plants and animals, but it also includes the millions of synthetic compounds created in modern laboratories.
And it's actually surprisingly simple to test the difference between the organic and inorganic worlds. If you take samples into a lab and heat them in air, carbon-based organic things generally burn. Think of, wood, paper, or oil catching fire. Whereas non-living, inorganic things like table salt or sand typically just melt or turn to vapor without actually burning. It's a really striking physical difference.
Now, with millions of organic compounds discovered, chemists have to classify them somehow, right? They do this using what are called functional groups. Whether it's an alcohol group featuring an oxygen and hydrogen or an ester, these functional groups are really just specific arrangements of atoms. They act kind of like the compound's personality, dictating exactly how a molecule is going to behave physically and chemically.
And these tiny carbon functional groups are the direct basis for massive real-world applications. I mean, this chemistry scales up to create almost everything. We're talking the life-saving pharmaceuticals in your medicine cabinet, the soap you wash your hands with, and the fuel powering your car. Even dry cleaning agents and the pesticides that protect our agriculture are organic compounds. They quite literally run our daily lives.
Section 2. Inorganic minerals and crucial acids.
Moving on to inorganic compounds. These are all the fundamental materials that make up the mineral constituents of the Earth's crust. They generally don't contain carbon and are typically found in nature as non-living things. To make sense of all this, chemists classify these inorganic heavyweights into 4 main groups: oxides, acids, bases, and salts. A prime example of an inorganic powerhouse is sulfuric acid. It is honestly staggering just how dependent we are on this one single chemical. It's the leading industrial chemical globally. It's responsible for producing the fertilizers that grow our food, the synthetic fibers woven into our clothes, our paints, our paper, and it even acts as the vital electrolyte in your car's battery. Without this specific inorganic acid, modern manufacturing would literally grind to a halt. Section 3. Electrochemistry and generating power.
So, electrochemistry is this fascinating relationship between electricity and chemical reactions. It's essentially a two-way street of power. On one side, we have electrolytic cells. These use electrical energy to actively force a chemical reaction to happen, which is a non-spontaneous process. But then on the flip side, we have galvanic or voltaic cells. These spontaneously use chemical reactions to create and release electricity. That battery in your flashlight or your smartphone? Yeah, that's a galvanic cell hard at work.
At the very heart of this energy transfer are the electrodes, usually metal strips or graphite rods where all the magic happens. You have an anode and the cathode. Oxidation, which is the loss of electrons, always happens at the anode. Meanwhile, reduction, which is the gain of electrons, happens at the cathode. And here is the beautiful symmetry of chemistry for you. The number of electrons lost at the anode is exactly equal to the number gained at the cathode. They always proceed simultaneously. Now, this isn't just theory to memorize for a high school test. This exact science of electron transfer is what makes our entire modern world portable and durable. Electrochemistry is how we run our dry cell flashlight batteries and automotive lead storage batteries, but it's also incredibly industrial. We use electrolysis to manufacture essential metals like aluminum and sodium straight from raw ores, to produce chlorine, and to purify and electroplate metals.
Section 4. Chemistry in Everyday Industry.
Every organic molecule, every inorganic acid, and every electrochemical reaction we've discussed today is scaled up by the chemical industry. Their goal is actually quite elegant: to utilize chemical processes to take raw natural resources, things pulled directly from the earth, and refine them into the commercial products that define and satisfy the needs of modern society. They literally build the foundation that other industries rely on to manufacture the items we buy and use every single day.
So, looking around your room right now, seeing how organic compounds, inorganic minerals, and electrochemical cells interact to build our world, I have to leave you with a provocative question. How many countless, unseen chemical reactions are sitting right in the palm of your hand? Think about the screen you're watching this explainer on right now, the refined metals, the synthetic organic polymers, the energy powering the display. It's all chemistry. It's a vast, dynamic system, and you are holding the results of millions of reactions right at this very second. Thanks for learning with the explainer today, and keep questioning the world around you.